Hello and welcome to your principal component analysis in Python lecture. So first thing, I'm going to run all my packages. So today we're going to look at the breast cancer data set, which is a data set we've looked at before. And we know that this data set has a bunch of different variables that describe features about the biopsy of a potential breast cancer. So let's load in our data, and I printed out the names of the columns, but we've seen a lot of these before. So it has like the radius of the biopsy, texture, perimeter, area, etc., all of this stuff. And it actually has a ton of different variables that we really haven't even looked at yet. So all in total, I think it has 29 of these continuous variables that we can look at. So I want to grab those. So I'm going to say features equals, and I'm going to make a list. So breast cancer, the data set, dot, and if you say columns, remember that's going to give you like a list of the names of the columns. And I want every column from 1, 2, 3. So I want to start at radius mean, and I want to end. I don't want this weird empty one. So I'm going to go, okay, from column 3 to 32, grab the names of all of those variables because those are the ones that I want to use. Now, another thing you might notice is that we have this weird column, and this is something that I've talked to some of you about, but let's just do it together. If you ever want to get rid of a column, you can do that using the dataframe.drop function, and you're going to say, what is the name of the column you want to drop? Mine in this case is unnamed 32. And then you're going to give it the variable or the argument axis. And in pandas, 0 axis means the rows, and the axis 1 is the column. So we want to get rid of a column, so we're going to tell it axis 1. So let's do that and then say bc.head just to make sure we did that correctly. Cool. So now we can see it doesn't have that weird column anymore. Okay, so now that we've done that, I'm going to now scale my variables. In fact, I'm going to standard scale. I'm going to z-score them. So I'm going to say z equals standard scalar. And the reason why, BC features, the reason why we want to scale these before we do anything is you can see that these variables are some of them on really different scales. And when you're looking at the variation in the data, the scale of the variable matters a lot. So we want to put them all on very similar scales. So I'm going to say BC features equals z dot fit transform, do it all in one step, BC features. Okay, so this is essentially just z-scoring all of our variables and storing it back into the data frame. Oh, it didn't like that. Hold on. Well, of course, it's because I already ran that. So there we go. Okay, so run this again. Now, let's just look at some of our variables really quick. So we can pull up a ggplot, and we'll say BC AES x equals radius, there we go, mean, y equals texture, my goodness, texture, there we go, texture mean, and then we'll make a geom point. Okay, so we're going to run this. So you can see, just like we talked about in the previous lecture with the the SAT and the GPA example, there is already just in these two variables, we're using 29 variables, just in these two variables we can see, oh, okay, there is some kind of relationship between these variables, and when there's some kind of relationship, we know that principal components analysis can usually take advantage of that relationship. Okay, so now that we've seen it, let's build our principal components analysis model. So luckily in sklearn it's called PCA, so that's not a lot to type unlike all of their other functions. And the way that we tell it, okay, we'll do principal components analysis is again with the fit function, and we're going to give it the variables that we want it to use, which is the features from the birth control data frame. So when we create this, it creates the principal components analysis model for us. Now we need to actually do something with that. So I'm actually going to copy and paste this. So one thing that we might want to look at, or a couple things that we might want to look at, are the explained variance from the model, which we saw in the previous lecture as our scree plot. So I'm going to grab that from the model. The way that you get the percentage of variance explained by each principal component is with the model.explained_variance_ratio_. And then I'm just putting that in a data frame. And this, by the way, I'm using something called a cumulative sum, which essentially says from the first variable, like how much is explained by just the first variable, then how much is explained by the second and the first, and then how much is explained by the third, second, and first, etc., over and over. So I'm storing all of that in a data frame, and you can see the printout of it here. And from this, I am going to make my scree plot using ggplot. So I'm going to say ggplot, and I'm going to say PCADF, AES. So on my x-axis, I'm obviously going to have my principal components. On my y-axis, I'm going to have my explained variance. And then I'm going to say plus geom point, and then plus geom line. Oh, I need to put those in quotes. There we go. Okay, so you can see this scree plot that we've had from before. So this scree plot says, okay, the first component accounts for almost 45% of the variance, and the second one accounts for almost 20. Then this one about 10, this one about, I don't know, 7, etc. And so when we look at these scree plots, it might be helpful in helping us decide how many principal components do we need to keep. We know we don't need to keep all of them because look, when you get up into like 20s, 20, 30, whatever, these explain almost zero variance, so we can probably chop those. But how do you decide how much is enough? Well, one method is to look at the scree plot and use something called the elbow method. So when you look at a scree plot, you're going to find what's called the point of inflection. And it's essentially like, where does the slope change from like a downward slope to kind of like, oh, we're going flat or upwards. And so that is probably here. When you look at the graph, it's like, where is the elbow of the graph? So in this case, it's probably like here. So that means we'd keep 1, 2, 3, 4, 5, 6 of the principal components. So that's one way of deciding. And basically that's saying like, how important are these? And when they start to get less important, the elbow method helps us find at what point are the principal components becoming a lot less important. The second way that we can do it is by saying, okay, there's a certain percentage of the information or the variance in the data that I want to keep, and let's just keep as many principal components as it takes to retain that amount of information. So this is what the cumulative sum was for. So this is similar to a scree plot. In fact, I've seen people make this plot and also call it a scree plot, you know, to each their own. So instead of saying what is the proportion of variance for each principal component, this is looking at across all principal components, how much of the total variation is explained in the first one, in the second and first one, in the third and first one. So like up until this principal component, how much of the variance is explained. So in this case, you can see that like the first two together are about 60 something percent. And then the first three together are like 73%. And then the first four together are almost 80%. And so what we can do is say, okay, I'm going to draw the line at 95%. I need the principal components that I choose to be describing at least 95% of the information in the data. So this black line is a line at 95%, and we can see that the first 10 components explain about 95% of the variation that we had in the original 29 variables. So in this case, when I make my decision, I would say, okay, I'm going to keep 10 of the principal components instead of all 29. Okay, so I'm going to copy and paste this code, but of course this will all be on GitHub for you to see. But I just want to show you. So what I'm doing is I'm pulling the principal components from the data. In this case, I'm pulling only the first 4. In this case, I'm pulling the first 10. And the reason I decided on those numbers is if we go by explained variance, the first 10 is going to be like explaining 95% of the variance. If we go by the elbow method, I probably would only keep the first 4. So that's just why I chose it. We could do any number though. And what I'm going to do is I'm going to build a logistic regression model that predicts malignant or benign in this data set using either all of the data, which is what this first model does, or using the first 10 principal components, or using the first 4 principal components. And when I run this, you can see I'm printing out the accuracy for these different models. So you can see when we use all of the data, we actually have really, really high accuracy. But remember, all of the data means 29 separate variables, which is a lot. When we look at the first 10 principal components only, you can see that we still had a pretty high accuracy, almost 80%. And similarly, when we used only 4 principal components, we had still a relatively high accuracy, about 72%. So, you're losing some information when you do principal components analysis, and that's just unavoidable if you don't want to keep all 29 variables. But look, the jump in accuracy is not that big. To go from 29 variables down to 10, we're only sacrificing a little bit of accuracy. And when you get to bigger models with more variables, the difference between the accuracy gets smaller and smaller. Okay, so just to review, basically what I'm trying to hopefully show you here is that when you're using just a couple of the principal components, you still are getting a lot of the information in the data. We went down from 29 to 4 variables, and in 4 variables, we still had 70% accuracy, which I think is incredibly good for 4 variables. So the last thing that I want to show you is not something we'll use a ton, but if you're interested in how the variables are relating to each other, this is something you want to look at. So I'm going to copy and paste, but again, all this is on GitHub if you need it. What I've made here is a table. In this variable column, this is all the 29 variables that we used. And in the loading column, this is essentially a measure of how strongly correlated this variable is with the principal component. So right now we're looking at only the first principal component. So when you look at these different, we'll call them loadings, when you look at these different loadings, you can see how strongly related each variable is to this factor, this component. So for instance, the texture mean has a loading of 0.1, which is a little bit less than the perimeter mean, which is 2.2, which is a little bit less than, let's see, the concavity mean, which is 0.226, whatever. So you can see that the variables that have higher loadings are more related to this component. So essentially what we would do is we would go, okay, which variables have the highest loading for this component? And those are the variables that we think are most strongly related to this component. So for example, in the baguette paper, when they said the first component was the process, what they probably did was made a chart somewhat like this, and they said, okay, which variables are the highest, like the most related to this component? Oh, it's all the variables that are about how the bread is baked. Okay, we'll call this the process component. And that's probably how they did it. Okay, so yeah, we won't do this a ton, but in case you're ever interested in that, that's how you would look at that. Okay, so I'm going to leave it there. We will do the rest in class together. Hopefully that makes sense, and I hope you've enjoyed learning about principal components analysis because it is one of my favorite things in the entire world. Okay, we'll see you next time.